At this point, we've seen two sorting algorithms, selection sort and insertion sort. They're both big O of n squared. Slightly different best case scenarios, but they're both, in the worst case, big O of n squared. So here's a question for us, is can we sort in better time than O of n squared? So as I said earlier, it's not great, it's not terrible, but as n gets really big, we don't want things to grow with the square of the input. And so we're going to talk about some algorithms that do better than big O of n squared. We're going to talk about merge sort, and then we're going to talk about quick sort, both of which are better than n squared. And I won't reveal just how much better, but we'll get to that in a little bit. So let's talk about merge sort first. Okay, so let me start by, instead of doing the full-blown sorting algorithm, let me talk about something called linear time merging. So linear time means it is not n squared, it's linear, it's n. But I'm not going to build the full sorting algorithm yet. I'm going to build the building blocks of the sorting algorithm, and in the next segment, I'll actually use this to do a full-blown sort. So let me describe what I mean by linear time merging. Imagine I give you a list with 10 elements in it. The first 5 elements are in sorted order, 2, 3, 6, 9, 10. And the second 5 elements are in sorted order, 1, 4, 5, 7, 8. But they are not in their entirety in sorted order, of course. Okay? So my job is to figure out how do you take this part that's sorted and this part that's sorted and create a single merged sorted list. Now notice this is not a full-blown sorting algorithm because these are already sorted and these are already sorted. So my job here is simply to take two sublists of equal or almost equal size and merge them, that's why I'm calling this linear time merging, in linear time, right? So sub-polynomial. So let's see how we're going to do that. So I take my first 5 elements, my second 5 elements, and I'm going to throw them into this two-dimensional array. So let's take 2, 3, 6, 9, 10 and put it in the top here. This is just for us to visualize it. You don't have to literally do this. And let's take 1, 4, 5, 7, 8 and put it along the bottom. Okay, so again, these 5 elements are sorted, these 5 elements are sorted, and my job now is to create a single sorted list of 10 elements that is all of these in the right order. Okay, and I want to do that in linear time. Okay, so how do I do that? Well, can we agree that the smallest element in the final merge list of 10 elements must either be this element or this element? Well, of course, this list is in sorted order along the top, and this list is in sorted order along the bottom. And so that means one of these two elements is the smallest element. So I don't actually have to do that much work to figure out what is the element in the first position here. I look at the first 2 elements of the 2 lists, and I say which one is smaller, and I take that and put it into the first position of the merged list. Okay? And now I repeat. I take, well, not the first 2 elements, but this one's been eliminated, so it's now wherever the position is. So I look at the 2 and the 4, and I ask, what's the smallest element? Well, it's 2. Well, that must be the second smallest element in the entire list. Why? Well, because they're both sorted, right? So there is nothing smaller than 2 or 4 in this entire list, and of course 2 is the smallest one. So I pop that up. Now, compare 2 more elements, 3 or 4. Well, 3 goes up. Compare 2 elements, 4, 6. So you see that there's this leading edge coming out this way, and I'm always only looking at 2 elements on every iteration. Yeah? Don't have to look at anything else. So the 4 pops up, the 5 pops up, the 6, the 7, the 8, and then of course I just pack in those last 2 elements. Okay, so let's just think a little bit about what is the runtime complexity of this. Well, I had 2 sorted sublists. How did they get sorted? Let's not worry about that now. We'll do that in the next segment when we actually build merge sort. I packed them into 2 sublists, and what did I have to do? I had to basically look at 2 elements that cost me 1, and then 2 elements that cost me time 1, 2 elements, 2 elements, 2 elements, 2 elements. And how many times did I have to do that? Just n times, right? That's what the whole list is, right? So the cost of this is linear in n. And the reason is that every time I put an element in here, I only had to do one comparison. And so this cost me 1, this cost me 1, this cost me 1, and there was a linear time of those in n. So, and of course the reason is that when I looked for the minimum element, I only had to compare 2 elements. I didn't have to look through the whole list. Well, because they're sorted. How did they get sorted? I have no idea right now. We have to build merge sort. But here's what we know, and there's something cool here, is that if I give you two lists that are sorted, sublists let's call them, I can create a single final merged list that is itself sorted in linear time. Okay, now that doesn't mean we have a linear time sorting algorithm, but it means we have the building blocks of something maybe that's going to be better than polynomial or square time. So let's take that concept of linear time merging, taking two sublists that are themselves sorted and creating a final complete sorted list that runs in linear time, and build a sorting algorithm. And we're going to pick that up in a few minutes when we do the next segment. So I'll see you in a minute.